Lifetimes are the single most common reason developers give up on Rust. Not ownership. Not the borrow checker in general. Specifically, the moment when the compiler starts asking you to write things like fn longest with a tick a parameter, or a struct with a tick a annotation, and you have no idea what any of it means or why you need it. I have seen developers with 10 years of C++ experience look at a lifetime error message and just close their laptops. So in this video I am going to explain lifetimes properly. Not just here is the syntax, but what they actually are, why they exist, the mental model that makes them click, and a fresh perspective from a QCon London 2026 talk that genuinely makes confusing lifetime errors intuitive. By the end of this video you will understand why lifetime annotations exist, when you need them, and when you do not, how to read and write them in functions and structs, what lifetime elision is and the 3 rules that govern it, what static actually means, and how to reason about higher-ranked lifetime bounds. This is the video I wish existed when I started learning Rust. Let's get into it. Before we dive in, I want to talk about Aarambh Dev Hub's partner, CodeCrafters, and this one I actually mean it when I say it is a good one. If you have been watching Aarambh Dev Hub for a while, you already know that we are all about understanding how things actually work under the hood. Not just using tools, but truly understanding them. Why does Redis work the way it does? How does Git actually store your commits? What is really happening when you type a command in your shell? CodeCrafters is built around exactly that same curiosity. CodeCrafters is a platform where you rebuild real developer tools from scratch. Things like Git, Redis, a shell, an HTTP server, a DNS server, a BitTorrent client, you actually build them yourself, stage by stage, in your own language. Every stage unlocks the next, and you can see exactly how far along you are as you go. Now the most popular language on CodeCrafters is Rust, and that makes total sense for this channel. If you're just getting started with Rust and want to learn it the right way, this is honestly one of the best approaches out there. Instead of reading theory or doing small exercises that go nowhere, you sit down and build something real. Something you have actually heard of. Something that exists in the real world. And that is when Rust really starts to click. This is not your typical tutorial platform where you just watch someone else code and feel like you learned something. You are the one writing the code, you are the one debugging it, you are the one making it pass each stage. That kind of active, hands-on learning is what actually makes you a better systems programmer, and I will be honest. It is genuinely a lot of fun. The challenges are used by engineers at companies like Google, Meta, and Shopify. And if your company has a learning and development budget, there is a very good chance CodeCrafters is covered under it, meaning it could cost you absolutely nothing out of pocket. Worth checking with your manager before you pay yourself. The link is in the description below. Check it out, and if you do sign up through it, you also directly support Aarambh Dev Hub, so thank you in advance if you do. Alright, now let us get into the video. Let me start with the most important thing I can tell you about lifetimes, and it is something almost every tutorial gets wrong. Lifetime annotations do not change how long a value lives. They do not control memory. They do not affect runtime behavior in any way. A lifetime annotation is purely a communication to the compiler. It describes the relationships between references, so the borrow checker can verify that your references are valid. That is the entire purpose. Think of a lifetime as a name for a scope. When you write tick A, you are giving a name to some region of code. When you annotate references with tick A, you are saying these references are related. They all refer to data that lives at least as long as this region. The compiler uses those annotations to check whether you are trying to use a reference past the point where the data it points to still exists. The reason this matters is that Rust has no garbage collector. There is no runtime scanning for dead references. If you could return a reference to a local variable that gets dropped at the end of the function, you would have a dangling pointer, a pointer to freed memory. The lifetime system catches this at compile time, not at runtime. Let me show you exactly the problem lifetimes solve before we look at syntax. This function compiles without any lifetime annotations. The compiler figures it out automatically. The returned reference clearly comes from S, so its lifetime is tied to S. One input reference, one output reference, obvious. Now watch what happens when we have 2 input references. The compiler rejects this with an error that tells you exactly what is wrong. This function's return type contains a borrowed value, but the signature does not say whether it is borrowed from X or Y. Think about what the compiler needs to know. If you call this function and get a reference back, that reference points to either the data behind X or the data behind Y. The compiler cannot know which at compile time because it depends on a runtime condition, so it cannot know which of those values must still be alive when you use the returned reference. This is precisely when you need a lifetime annotation. The tick is a generic lifetime parameter. By marking both inputs and the output with tick you are telling the compiler that the returned reference will live at least as long as the shorter of the two inputs. Now the compiler can do its job. It knows that as long as both X and Y are alive, the returned reference is safe to use. If this is finally making lifetimes click, hit the like button. It genuinely helps this video reach more developers who are stuck on exactly this. Subscribe for more deep dive Rust content every week. Back to it. Here is a mental model that works better than the traditional scopes and regions explanation. It comes from a QCon London 2026 talk by Ethan Brierley, a senior engineer at TrueLayer. Rather than explaining lifetimes as regions of code, Brierley built his talk around the Polonius borrow checkers model where lifetimes are treated as sets of loans. In the Polonius model, a lifetime tracks all the possible places a reference might have originated. Each origin is a loan, and loans carry terms that must not be violated while the reference is alive. Think of it like a library book system. When you borrow a reference, you are taking out a loan on some data. That loan has terms. You can read the data, but you cannot modify the original while the loan is outstanding. Borrow checking becomes a line-by-line exercise. Figure out which loans are live at each point in the code, and check whether anything on that line violates the terms of any outstanding loan. He compared the two mental models to solving a maze. You can think about the pathways through it, or the walls. Both get you to the same answer, but focusing on the walls can unlock understanding that the pathway view doesn't. Let me show you how this makes a classic error intuitive. In the loans model, Y creates an immutable loan on X. That loan is still live on the println line because Y is used there. On the line in between, X gets mutated. That violates the loan terms. Error found. More intuitive than thinking about overlapping scopes. Here is something most lifetime tutorials explain poorly. You do not need to write lifetime annotations in most Rust code. The compiler infers them through a set of rules called lifetime elision. There are 3 elision rules. If the compiler can determine lifetimes by applying these rules, you do not need to write them explicitly. If it cannot, you must. Rule 1. Each input reference gets its own distinct lifetime. If a function takes 2 reference parameters, the compiler assigns them separate lifetimes internally. Rule 2. If there is exactly one input lifetime, that lifetime is assigned to all output lifetimes. This is why get first word compiles without annotations. One input, one output, same lifetime. Rule 3. If one of the inputs is on self in a method, that lifetime is assigned to all output lifetimes. Let me show you each rule in action. Rule 2, one input, compiler handles it automatically. Rule 3, method on self, compiler handles it automatically. 2 inputs, no self. None of the 3 rules can determine the output lifetime, so you must write annotations. Once you know the 3 rules, you can look at any function and immediately know whether you need to write lifetime annotations or whether the compiler handles it. When a struct holds a reference, you must annotate it. This is the part that trips people up when they first try to store references inside structs. The tick on the struct means a user cannot outlive the data that name points to. When you create a user, the compiler enforces that the string behind name stays alive at least as long as the user does. The common mistake is trying to return a struct holding a reference to local data. The fix is either to give user an owned string instead of a reference, or to ensure the data passed and lives long enough. Sometimes you genuinely need 2 different lifetime parameters. This is the pattern that looks scariest but has a clear use case. By using A for CTX and the return value, and B for pattern, we tell the compiler that the returned reference lives as long as the context. This means you can drop pattern while still using the returned reference, completely safe because the returned data comes from CTX, not pattern. If you used a single A for everything, the compiler would require all 3 to live equally long, which is too restrictive and would reject valid code. If you are working through lifetime errors in a real project and want to talk through a specific example, Come join the Discord, the link is in the description. We run a weekly Sunday study group and lifetime puzzles come up regularly. A genuinely helpful place to think through hard compiler errors. Link is below. The lifetime static confuses people most, partly because of its name. Static means the data can live for the entire program duration. But this does not mean the data has to be a string literal embedded in the binary. It means the compiler can prove the data will not become invalid for the rest of the program. Two things have static lifetime in practice. First, string literals, they are compiled into the binary so they live forever. Second, owned data with no borrowed references inside it. This is why threads require static bounds. When you see T, static as a generic bound, it does not mean T must be a literal. It means T contains no borrowed references that could become invalid. An owned string satisfies T static. A vec of owned values satisfies it. A struct with and star fields does not. The rule to remember, static does not mean this lasts forever. It means this contains no borrowed references that could become invalid. This is the advanced concept that scares people away from crates like serde. Let me explain it. When you write a function that creates a temporary string slice internally and passes it to another function, that temporary slice cannot be named in your outer function's signature. It originates inside the function body. The solution is the fora syntax says the type must implement a trait for every possible lifetime, not just a specific one. This is different from writing a named lifetime parameter, which would tie the closure's capability to one specific scope. The fora says it works universally. In serde, DeserializeOwned is essentially sugar over a higher ranked bound that says this type can be deserialized from a string slice with any lifetime. That is what allows you to deserialize into owned types like string without the lifetime of the borrowed input string leaking into the deserialized output. You will rarely need to write for yourself. But when you see it in trait bounds, you now know what it means works with any lifetime, not just a specific one. Let me close with 5 things that will make every future lifetime error approachable. 1. Lifetime annotations describe relationships between references, not how long things live. They are communication to the compiler, not memory management. 2. Most lifetimes are inferred through the 3 elision rules. You only need to write annotations when the compiler cannot determine the relationships itself. 3. When a struct holds a reference, annotate it. The annotation means the struct cannot outlive the data it borrows. 4. When you have 2 input references and the output could come from either, tell the compiler which one the output comes from. That is the entire purpose of explicit annotations. 5. Static does not mean forever. It means contains no borrowed references that could become invalid. If this video finally made lifetimes click for you, and you want to support the channel, buy me a coffee. The link is in the description. It goes directly toward building these explanations and making these videos. Thank you genuinely to everyone who has already. That is Rust lifetimes fully explained, what they actually are and are not, the loans mental model from QCon London 2026, the 3 lifetime elision rules, lifetime annotations in functions and structs, multiple lifetime parameters for complex relationships, what static really means, and for higher ranked bounds demystified. Lifetimes are not the enemy. They are the compiler asking you to be explicit about relationships that other languages leave implicit and unsafe. Once you have the mental model, the annotations go from cryptic to obvious. If this video cleared up lifetimes for you, hit the like button. It helps this reach more developers who are stuck. Subscribe for more deep dive Rust content every week. Drop a comment, which lifetime error stopped you most recently? I read every single one. Check out the Rust FFI video and the 10 Rust mistakes video for more deep Rust concepts. Both are linked in the description. Join the Discord community, link in the description. And support via Buy Me a Coffee, also linked. Thanks for watching and happy coding.